So now let's move on to what we actually solve and how we actually get a solution. Our practical algorithm. And then I will explain how this fits broadly into the whole range of different methods for regression and supervised learning more generally. So the final form of our learning problem or learning objective, the one that leads to a practical algorithm, we call empirical risk minimization. And as the name suggests, it involves minimizing the empirical risk, not the risk, which we cannot do because we don't know the distribution of the random pairs. But what we do have is a data set, so why don't we minimize the empirical risk with one other caveat? So what do we have? We have data, and we are considering these as realizations of IID random pairs. So number one, choose a loss function. Number two, choose a hypothesis class. That's the caveat. We need to choose a loss function. So how do we measure best, closest error? And then we need to choose a hypothesis class. So these choices will have consequences. Then the problem we solve is this, and we call it empirical risk minimization, or ERM. Choose the best prediction rule in the following sense: the one that minimizes the empirical risk over all F only in our chosen hypothesis class. And explicitly, we are minimizing this realization of the empirical risk. So we are finding the function F only in this hypothesis class that minimizes this arithmetic mean of these realizations of the loss, or the empirical risk, realized empirical risk for this data set that we have. So you can see here that learning is essentially now an optimization problem. We are just minimizing this. But how do we turn this into a practical problem? Because we still don't want to be minimizing over functions, doing anything like calculus of variations. So let's have a look at how we typically do it in practice, at least in parametric cases. If we have a parametric hypothesis space, then what are we doing? We have a function, all of the functions in F look the same. They are only distinguished by the values of the parameters, and there are a finite number of parameters. Let's say that these parameters, collectively we call them theta, and they look like this: theta 1, theta 2, up to theta p. Let's say they all lie in some space theta, right? And this space is just some subset of Rp, the subset of the Euclidean space. I guess technically I should put that transpose there, right? I've been a bit lazy about this. Watch the linear algebra videos. I mean, we can always write them like this. Just consider them as n-tuples. But once we put them in a coordinate form, we think of them as column vectors, right? And they're equivalent, right? So we are, rather than now minimizing over whole functions, we only need to find the best theta, not the best function, the best theta, because all of the functions depend on these p parameters. The only thing that changes is the value of the parameter theta, the values of these. So rather than finding the best f, we equivalently find the best theta. So we find theta hat that minimizes the empirical risk over all functions f theta, where theta is in this set theta, of allowed values of theta. Because there could be some values in here which are just ridiculous. So we normally confine the values to some feasible set. And written out explicitly, it's this arithmetic mean of these realized losses here, right? That is our empirical risk realized using our realization, which is our data set. Okay, so obviously this is a much nicer problem. We are now minimizing over some finite dimensional vector space, right, or subset of it. But two things to note here, and then I will finish this off and we will start to look at practical solutions. Our best, meaning the Bayes optimum, which was defined like this, might not be in our hypothesis space, right? There's no guarantee at all that it will be, and it may be very far away from that. So, for example, we might use a hypothesis space of linear functions, whereas the true or the best prediction rule or predictor is actually some much more complicated nonlinear function. But we're only looking at functions that are linear or affine. Well, we're going to have a huge error, and that error is approximation error. More fundamentally, how do we justify using this empirical risk to estimate the true risk? And that's something we will come to much later on. But I will end here by saying one thing. So we are looking at what we call an ERM, Empirical Risk Minimization Framework. There are different ways to approach regression and supervised learning in general. This is the 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 broadest way we can do it. All other approaches will fit into this framework, which is why not just supervised learning, but other forms of machine learning are presented in this way. But especially, I would say supervised learning is presented as empirical risk minimization, because all the other approaches, and we will look at them, ordinary least squares, maximum likelihood, will all lead us to the same place, and they are special cases of empirical risk minimization. In fact, even generative approaches, or the ones that we would consider in regression, are special cases of empirical risk minimization. This is why this language is so common of losses, risks, and empirical risk minimization. It is the broadest framework, the framework within which we can place everything else as a special case. However, these other approaches may have different motivations, or at least original motivations. So we will start when we start looking at, for example, maximum likelihood by talking about this problem from a different point of view. And then in the end, I will show you, well, this actually turns out to be, at least in the special cases that we look at, empirical risk minimization. So that's what I wanted to say about this, and why we're taking this, why I am taking this approach of teaching you regression and supervised learning.